Okay, this is section 2.9. This is more mathematical modeling. Take a second to watch this video on mathematical models. One of the keys to mathematical modeling is mathematical models involve equations. At this level, pretty much it's you make an equation for a model, but sometimes modeling can involve multiple equations coming together. Um, so It's often a powerful technology that can play a major role in modern methods of predicting and modeling, but there's some things to be aware of as well. Okay, we'll talk about some of the cautions coming up. So we're going to talk about the exponential model and the half-life. So we've got a graph here, y equals e to the x. Notice it's very zoomed out on the y-axis, so it looks very flat on the x-axis at first, because this is 2000. Um, e to the negative x is going to kind of go the opposite way. And we can develop a formula. So if we know our basic exponential is, hold on a second. So if my basic exponential model is y equals ab to the x, or you'll see it in this book as y equals a0 e to the, well, they're using lambda. I'm going to use k. I like k better than lambda in this situation. So we can think of our half-life as half of the initial amount. So if I want to solve this, I can divide both sides by a0. I don't know, 1 over a0, which will cancel those, leaving me with this beautiful little simple equation. 1/2 equals the zeros cancel e to the negative kt. So I ln both sides to get rid of this e, and that equals negative kt. The time for the half-life is to divide by negative k. Now here's this really nice trick. You can use the laws of logs. ln 1/2 is ln 1 minus ln 2. They're not showing this, but this is a pretty common way of doing this. ln 1 is 0. So if 0 minus ln 2 just becomes negative ln 2 over negative k, which equals ln 2 over k, and that was equal to my time for my half-life. Often we use it, we know the half-life's time, so we'll solve for k. But it can work either way. Okay, so using this, ln, looking at my first example here. After 1,000 years, we have a sample of radium-226 that's decayed to 64.7% of its original mass. Find the half-life. Okay, so we don't know the time of the half-life. We don't know the K. But we do know that it's decayed to 64.7% of its original mass. So I can use my equation and set it to 0.64780. And then when I divide by a0 on both sides, the a0's just cancel. And I get 0.647 equals e to the negative kt. So to solve, I take the natural log of both sides. And when I take the natural log of e to the negative kt, I just get negative kt. Oh, I guess I knew t was 1,000. So I'll divide this by t to get negative k. And we're going to do put the negative there. 1,000. Divide both. So now it asked me to find the half-life. Which could be, I'm going to plug this into the calculator. Effectively, I'm going to multiply by the reciprocal because it'll be a little easier. I need to be on a calculator screen. Negative 1,000 times ln2 divided by ln 0.647. My half-life is 1,592 years. Or if you're going, I guess 3 sig figs, which is pretty normal for this, would be 1,590. Oh, they rounded off. I don't like this. I don't like their 1,593 because they rounded here. Yeah, it should be 1,592. I think if you plugged it in like this and showed that, they'd take either answer. But 3 sig figs of 1,590 should be okay. Okay, more models, different types. Okay, there are logarithmic models. So here we've got a bunch of data, and we can tell that makes a generally logarithmic shaped graph. On the scatter plot. So to match the first point, you need to take, what they're doing is they're taking a plus b ln x. And when you plug in x, they're taking, so they're writing these two equations, plugging in x and y, which when you have a set of equations like that, we can make this into a system. And we can solve for a and b. It happens to be very easy that ln1 is 0. So this just becomes a is 202,000. And b, then we can just solve for, and we get this. So we plug that in for a because ln1. Now we plug this into the second equation. Solve for b, you get that. And then finally, that becomes approximately your model going through those 2 points. We could also model via graphing calculator. But it's important to know that you can model using a pair of points and get an approximate. I'd say you'd get a better model if you use the logarithmic regression, but you can look at that one versus the f of x down here. They're not that different. Um, you can get sinusoidal models. Okay, keep in mind they're in this form. Not positive if the Sometimes the phase shift will be this, and I'm not positive how the graphing calculator does it. Where it has the C not factored out. If the C is not factored out, you just do C divided by B. I like the factored out form. I think it's nicer and cleaner. So here we have this table shows the number and thousands of species of fish to start over 24 years. Why do the numbers oscillate? Find an approximate sinusoidal model. Why do they oscillate? Food and predators tend to come and go, and the more food there is for the predators, the more predators come, so they eat more fish, which brings it down. As the fish level goes down, the predators don't have enough to eat, so they die off, the fish comes back up. Or it could be food. The fish increases in population as the food thrives, they eat too much of their food, and some of them start to die off because there's not enough food. So the population declines a little bit. As the population declines, the food supply grows back stronger. And so the population can go because there's more food. So to do this model on the calculator, I'm going to go to my calculator. I have a list and spreadsheet open. Um, year of here's 0, 2, 4, 6, 8, 10, 12, 14, 16. I have to scroll sideways on this table. I'm looking at it on another screen. 18, 20, and 22. Ten point two, 11.1, 12.7. Wait a second. And getting mixed up in the multiple of these are lining up with each other. Oh, this is way too perfect of numbers. They're just repeating each other. Oh no, finally didn't repeat. Okay, so now I've got my numbers in here. I put year on the x-axis and population on the y-axis, and I see a pretty good sinusoid. And I can just do menu, analyze, regression, show sinusoidal. And I can't see the whole thing. So this becomes my model. Y equals 1.00466 sine 0.575 x minus 1.041. Notice that this is not factored out, so I will have to do the B over C for that. Plus 11.0. So here's my model. I guess they chose to find the model by hand. I don't think I ever would. But they decided the period repeated every 11. It's interesting. And then it was shifted to 1.5. Okay, yeah. So the amplitude became pretty easy to find. The high point and the low point was 10 and 12. You can kind of assume that, but maybe not guaranteed. Um, so A is 1, D is 11. D is definitely 11. The amplitude was 1, so and that's approximately what we got with the calculator. The minimum seems to be 10, and this occurs in year 10, and once again in year, they said 21 because it's halfway between the 10.2s. So that's how they got 11, 2 pi over 11. The period's 11 was 2 pi over b. If you solve that, you get b equals 11 over 2 pi. Now, you multiply both sides by b and then you divide by 11, 2 pi over 11. Yeah, which is what they had. And then to get to 11, they needed a phase shift of 1.5 to the right. And they approximated it as 1.5 because it came, if you look back at your data, it falls somewhere between 0 and 2 to where it crosses 11. Um, a logistic model. We know that logistic, the carrying capacity is this top number. I usually put C up there and this is A, but whatever. The maximum growth point is kind of in the middle, right here. And usually the lower asymptote's 0. You can do a vertical shift to move the lower asymptote if you need to, but I don't think they do in this course. Just put a plus D on the end. So how does L affect it? L, if you're looking at it, raises and lowers the carrying capacity. The C is going to you don't want to go to 1 because that's just going to flatline that whole thing. But I know you don't want to go to 0 because it'll get rid of that whole term. But C is going to shift it left to right mostly. And K is going to affect how steeply it grows. So this is affecting the steepness of the growth, basically how strong is the exponential. C mostly shifts it left, right. And then L affects the upper bound. Okay. Following is part of Verhulst published in his second paper on the logistic curve to model population growth. Okay, so this is the population of Belgium. Draw a scatter plot and comment on the trend. So we're going to put this in the calculator and do all of these. Um, to do this by hand, we could do this with these 3 points. Okay, draw the model on your scatter plot. So they're essentially showing you doing this by hand. Use the logistic regression on your calculator that also considers the other data points and comment on the difference between the 2 models. So we're just going to look at how they did it by hand. So here we've got it. It actually looks pretty linear here, but they plugged in values. Okay, so we've got this. And if you multiply both sides by the denominator, you end up with this. And then, so you end up with L equals, and you do that with all three equations. You can set the L's equal to each other, and then you've got two equations with two unknowns. You can solve those by using a little bit of a screwy system of equations here, but here they've distributed, they put the C's together and factored them out. So you take this line right here, you move this to this side and this to this side, and then you can factor out a C, and you get C equals this when you divide. Now, if you plug that in, you can do the same thing on the other one. And then you're probably going to have to set them equal to each other and solve via the graphing calculator. They put it into a ratio, but you still need to solve via graphing calculator, which to me kind of defeats the purpose of why did we do this by hand, other than it is a good exercise to be able to realize that you can this combining, setting things equal to each other. That's an important exercise. We end up with this model here. So this is how it was first done when to use population models before they had graphing technology that could consider other points and do it for us. So with our graphing calculator, we just go ahead and we enter all the data. So I need to come back up here. Actually, I'm going to look at the data on another screen, but here's my data. They picked what when they picked their data, they did one at the beginning, one in the middle, and one at the end. So I'm going to go to my calculator. I'm going to start a new one. No, I don't need to save it. They did every 5 years except they missed 1820. Sometimes it's a good idea to like go like 15, 25, but they did not for the sake of this model, so I'm not going to because it won't match theirs. If it doesn't tell you on a test, do not. Also helpful to enter it in the correct box. Okay, so now that we have our data entered, we will add a data and statistics page. Put year and population on the axes. Then we do menu, analyze regressions, show not logarithmic. Logistic. We did not have a D in the last one, so we're going to know D equals zero. So the D equals zero versus D equals not zero allows D equals not zero allows you to have the lower asymptote not on the x-axis. So we get the same model. It's similar but slightly different. The You can put them both on the same graph. And we see that when they're both on the same graph, we see they're pretty close. So, and we have red and blue. We enter another point. The current population of Belgium is higher than the carrying capacity predicted by previous models. So if we add that, we get a new model, which is this blue one. Okay? So notice that 2020 is a long ways from the previous data, 1845. One key thing with mathematical models, and this is a theory of knowledge connection, is models work great near the area that they're in. But a lot of times things change. The reason patterns and growth patterns change, and they allow us to see models that end up being drastically different than what we predicted when we go far into the future. Extrapolation is what it's called, predicting into the future, and that is a dangerous concept, often leads to very inaccurate things. Sometimes we have to extrapolate to predict into the near future or trying to predict the long-term future, but it's important to understand the limitations on the accuracy of extrapolation. Okay, that was section 2.9.